So where exactly is a quantum particle? It sounds like a super simple question, right? I mean, if I toss a baseball to you, you know exactly where it is and exactly how fast it's going. But down in the quantum realm, yeah, that totally intuitive everyday reality completely breaks down. We're suddenly forced to figure out how to locate something that fundamentally exists only as, well, a probability. How in the world do we build a tangible physical universe out of spreading, rippling waves?
Welcome to The Explainer. Today, we've got an incredibly ambitious and honestly, absolutely fascinating goal ahead of us. We are going to translate dense quantum math into an intuitive visual reality. We're looking right at the Schrodinger equation, but hey, not as some intimidating string of algebra, but as a dynamic blueprint for how the universe actually operates at the subatomic level. By the time we wrap this up, you'll literally be able to read a quantum state.
To get there, we've got a really clear roadmap. First up, classical versus quantum worlds. Then decoding the wave function. Third, we'll tackle the shooting method. Number 4, building a quantum particle. And finally, number 5, the uncertainty principle. Let's jump right into section 1, classical versus quantum worlds, two different realities. Okay, let's ground ourselves in the familiar before we totally pull the rug out. Picture a classic physics setup, a standard mass attached to a spring. In our good old classical world, if we know the total energy and the potential energy, boom, we can perfectly predict its trajectory. It's like clockwork. But glance over at the quantum wave side of things, and we literally can't do that. We can't know the exact position and momentum at the same time. Instead, our particle state is this probabilistic, complex, spread-out wave. It doesn't live in just one neat little spot anymore. It lives in an entire space of likelihoods.
Moving on to section 2, decoding the wave function, reading the quantum graph.
So how do we actually read these wild quantum graphs? Well, a massive key here is a concept called curviness. Yes, curviness. When you're looking at a quantum wave function, how much it wiggles or oscillates actually whispers a physical secret to you. The greater the curviness, meaning the tighter and more frequent those oscillations are, the higher the average kinetic energy of the system is right there in that region. So when you see a wave function bunching up with a ton of sharp curves, you are quite literally looking at a higher energy state.
Now keep in mind, these aren't just your standard ocean waves. They're complex functions packing both real and imaginary parts. To actually visualize them, we focus on two main things, amplitude and color. The amplitude, or simply the height of the wave, gives us the probability density. Basically, where are we most likely to actually find this particle? Then there's color, which acts like a map for the phase of this complex wave function. As the clock ticks forward in the quantum world, this phase evolves, and the colors smoothly change as the phase rotates clockwise in the complex plane. It's really quite a beautiful system. The absolutely crucial thing to understand here is what happens when a particle gets trapped in a specific energy level, what we call an energy eigenstate. In these particular states, the amplitude of the wave function, it stays completely frozen over time. The probability of finding the particle in a given spot simply does not fluctuate. Because literally only the color, just the phase, is changing as time goes on. We call these stationary states. Which brings us to section 3, the shooting method, finding the right energy. So if only specific mathematical energy levels give us these perfect stationary states, how on earth do we actually find them? Well, we use a super clever numerical algorithm called the shooting method, and it is surprisingly logical. Step 1, you literally just guess an initial energy value. Step 2, calculate the wave function from left to right based on that guess. And step 3, you look way down at the very end of the wave. For a bound particle to mathematically exist, its wave function has to drop completely cleanly to 0 at infinity. So you just check your work. Did your wave land perfectly on 0, or did it totally overshoot? This illustrates so brilliantly exactly why only certain energy levels, the eigenvalues, are allowed in quantum mechanics. Look at it this way. If your initial energy guess is too small, the wave just doesn't have enough of that curviness we talked about to reach the axis, so it undershoots. On the flip side, if the energy is too large, you get way too much curviness and it wildly overshoots the axis. It's only that exact, perfect, correct energy, the eigenvalue, that creates a wave that gently taps exactly 0 at infinity. It is the ultimate quantum Goldilocks scenario, and it is exactly why quantum energy is quantized. All right, section 4. Building a quantum particle from waves to reality. Let's take all this and see what happens when we remove those boundaries entirely and just release the particle into free space. A free particle following the Schrodinger equation gives us what's called a plane wave. Now, a plane wave has a perfectly defined momentum, which is great. But here is the massive catch. Its amplitude is identical literally everywhere across infinite space. The probability of finding it is completely unlocalized. So if we want to get something that actually behaves like a classical particle that we can measure in a lab, we need a wave packet, basically a localized grouping of waves.
Which leads to a bit of a brain teaser. Think about it. If a single plane wave is spread out evenly across the entire infinite universe, how on earth do we build a particle that actually exists in just one localized place?
The answer is mathematically stunning. We do it by adding a massive continuum of different plane waves together, all governed by the magic of the Fourier transform. By layering an infinite number of waves on top of each other, each with slightly different momentums, their peaks and troughs start to cancel each other out everywhere in the universe. Everywhere, that is, except for one tiny, specific, localized spot where they all constructively add up together.
I really want you to just pause and think about the sheer mind-bending scale of what that means. A localized wave packet can be constructed out of an infinite number of plane wave solutions of the free particle Schrödinger equation. The reality of a single localized particle sitting right in front of you is quite literally built from an infinite chorus of waves spread across all of space, harmonizing perfectly in just one tiny little spot. No way, right? It's completely incredible.
And that brings us to our final act. Section 5, the uncertainty principle, the cost of localization.
But hey, the universe isn't just handing out perfect localized particles for free. There's always a cost. If you want a really narrow, highly precise position for your particle, you are absolutely forced to add together a massively wide spread of different momentum waves just to cancel out the edges. And conversely, if you demand a really precise momentum, you can only use a handful of waves, which instantly causes the position to blur and spread way out. You just cannot know both perfectly at the same time. This constant, unavoidable trade-off, that is the physical origin of Heisenberg's famous uncertainty principle. This leads us directly to the minimum indeterminacy wave packet. Simply put, a Gaussian wave packet is the absolute closest a quantum wave will ever get to being a classical particle. It sits precariously right at the mathematical limit of the uncertainty principle. It is the tightest, most perfect compromise the universe is willing to allow between knowing exactly where something is and knowing exactly where it's going. But here's the kicker. Even this flawless compromise doesn't last. Because our localized packet is constructed from so many different underlying plane waves, and because waves with different momentums naturally travel at different speeds, which we call their phase velocity, the packet inherently tears itself apart over time. The faster waves race ahead, the slower ones lag behind, and eventually the whole packet just smears out across space. The craziest part, the tighter you squeeze it initially, the faster it violently spreads out later. Which leaves us with a genuinely profound final thought. If, when left entirely to its own devices, a free quantum particle, the literal foundation of matter, inherently loses its localized structure and blurs right back into the probability of the universe, what does that mean for the solid, predictable building blocks we see around us every single day? It means our reality is a whole lot more active, delicately balanced, and deeply interconnected than we could ever possibly perceive with the naked eye.